All right, we're going to continue lesson 7 by talking about types of non-differentiable points. So non-differentiable points would mean places where we cannot take a derivative. The limit will not exist. And there are a couple of different types of these. The first one is what we often call them cusps. So cusps is the common term, and it's a corner or a sharp turn. So like a V, the point, the vertex of an absolute value would be considered a cusp. It's going to be different from if I keep doing that, don't I? If we had, say, a parabola, right? And we have a turning point. This is not a cusp. This is a nice, it's not really a great picture. There we go. This is a smooth transition. Okay. This is not. Okay. So the difference is if it really looks like a corner, then that would be a cusp. And if we're going to answer the question why is that not differentiable? It has to do with the limit. Oops. If I am doing secant lines, remember we're taking two secant lines, the slope between them, and then we're taking the limit as they get closer to each other, those 2 points. Look at what my secant lines look like if I approach this cusp from the right side. But if I were to approach it from the left side, I'm looking at completely different secant lines. And in fact, it's easier if I kind of get rid of those pictures. This one is coming to be very close to a positive, almost infinite slope, whereas on this side, my slope is really just the slope of this line, and that would be a negative number. So the answer for why are these things not differentiable is that the secant lines on one side will not agree with the secant lines on the other side. So basically, if you are doing this limit, when you approach from the right, it's going to be different than if you approach from the left. And when you have a nice smooth transition, that doesn't happen because if you can visualize, these lines are really just, as you go this way, are really just turning into that horizontal line. And same with the ones on the other side. Whereas here, I'm not approaching a horizontal line at all. So it's the sharpness of the point that creates that lack of agreement. So cusps, non-differentiable points. Vertical tangent lines. So any place, the slope of a vertical line does not exist. It's infinite. So any place where your tangent line would be vertical is going to be a non-differentiable point. We don't see those a ton, but they are there. And last but not least would be discontinuities. If you have a place, a function, a point where a function is not continuous, it cannot be differentiable there. If it's a jump, it absolutely, you're looking at two different functions, so there is no such thing as a tangent line. If it's an infinite, like a vertical asymptote, it's not even defined there. And same with removable. So if it's not continuous at a point, it cannot be differentiable there. So then I'll just write this. This holds for all discontinuities. Jumps, infinite, and removable. And that also leads us to the next question. is there a relationship between differentiable and continuous? Well, we just actually talked about one part of it. If a function is not continuous, it's not differentiable. So not continuous means you can draw the conclusion that it's not differentiable. And so we're actually going to just rephrase that in a more positive language, which says that if it is differentiable, then it is continuous. Okay. So if it is differentiable, if you know that it's differentiable, then you can conclude that it's continuous. If you know that it is not continuous, then you can say that it is not differentiable. But you cannot go in reverse. You can't say continuous means differentiable. And the most shining example of that is the standard cusp problem here. So if you think about the graph of the absolute value of x, is it continuous at 0? Sure. It's defined at 0. The two side limits match up. We're good. But is it differentiable there? No, because of the cusp. Okay. So I'm not actually going to go through and show this in a proof in this particular lesson, but we can either work on it in class at some class meeting, or again, you can look it up online. But that is the most classic example, is continuous at x equals 0, but not differentiable. Okay, so if you're ever wondering, like, how does that go again? Which one tells me which one? Think of the absolute value. Oh, that's continuous, but not differentiable. Okay, and then last but not least in this section, we're just gonna quickly, or lesson, we're quickly gonna talk about higher derivatives, which basically is a derivative of a derivative. You can take another derivative. So f prime prime, the derivative of f prime, which we write this way. Now it's got two tick marks, like quotes, and we call it f double prime. It's called the second derivative of f. It looks very funky in the dy dx notation, but d2y dx2, it is weird, I agree. Okay. But we can take a second derivative, and just to add, we'll do an example of it in just a second, but think about how that applies to our motion. Remember, we have s is position, v is velocity, and s prime is equal to v. S double prime, v prime, what would that be? How do you measure how your velocity is changing? What is the rate of change of velocity? Acceleration. Right. So in terms of motion, the rate of change of velocity is acceleration. And I'm just going to write it in this form here. I know I wrote it up there the same way, but okay. So just a quick example. We're not going to do too many of these in this lesson because you have to go through this limit process twice, which is definitely a pain. We are going to learn shortcuts to the limit process starting in the next lesson, but you are going to have to be able to do these derivatives with the limit process using the definition. So just because shortcuts are coming doesn't mean we get to ignore the last two lessons. So what we're going to do in this final example is we have a function and we need to find the second derivative. So we'll go through and find the first derivative first, and then we will do it again. So f prime of x will be the limit as h approaches 0 of f of x plus h minus f of x. Sorry for the color change. Just trying to just make my pen less thick. Okay, so let's begin the plug-in process. I need to plug x plus h into the original function. So all of x plus h into here would be this. And then I need to subtract f of x, which is just that original, oops, function, all over h. So the fun part is you are going to need to multiply this out, distribute a few negatives, but it shouldn't be too painful to do. You may remember some Pascal's triangle, which helps kind of shortcut multiplying out x plus h to the third, or you could just brute force method. Then I'm going to distribute my negatives. And let's look at what's going to cancel. X to the third is going to cancel. X is going to cancel. And I think that's it. So I will have the limit as h approaches 0. Now let's scan. By now, maybe you've realized that when you do this, an h always has to factor out to cancel with this. So what I have left, they all have an h in them. So I'm going to factor that out now. So that I can cancel the h's. And now I can plug in my h equals 0, which is going to make these two terms go away. And I should just have 3x squared minus 1. So that's my first derivative. Now we're going to do the process again, but on this function, we're going to find its derivative, and that is what we will call f double prime. So go ahead and pause, work that out, and come back. All right, give it a look. I just did all the algebra, multiplied it out, distributed my things, canceled what was opposite, factored out the h, and then plugged in the h equals 0. And my final answer was that the second derivative of that original function is equal to 6x.